Welcome back to Exploring Science Unleashed. In this segment, we'll delve deeper into the differences between atomic bombs and hydrogen bombs, as well as their distinct working processes. These two types of bombs are at the pinnacle of human destructive capability, but they operate on fundamentally different principles. The atomic bomb. The atomic bomb, often referred to as an A-bomb, relies on the process of nuclear fission. Fission involves splitting the nucleus of a heavy atom, such as uranium-235 or plutonium-239, into smaller fragments. This process releases an immense amount of energy, which is harnessed to create a devastating explosion. Fission chain reaction. Picture a domino effect, where the splitting of one nucleus triggers the splitting of nearby nuclei, leading to a rapid chain reaction. In an atomic bomb, conventional explosives are used to compress the fissile material, bringing the atomic nuclei close enough together to initiate fission. This compression causes an unstable nucleus to split into two or more smaller nuclei, releasing a massive amount of energy in the form of heat and radiation. The hydrogen bomb. Now, let's explore the hydrogen bomb, often called a thermonuclear bomb or an H-bomb. Unlike atomic bombs, hydrogen bombs rely on nuclear fusion, a process in which light atomic nuclei combine to form a heavier nucleus, releasing an even greater amount of energy than fission. Fusion reaction. Imagine two hydrogen isotopes, deuterium and tritium, coming together to form a helium nucleus and a neutron. This fusion process generates a tremendous amount of energy. However, achieving the conditions necessary for nuclear fusion is incredibly challenging, as it requires extremely high temperatures and pressures. The working process. The working processes of atomic and hydrogen bombs are distinct, reflecting their reliance on different nuclear reactions. In an atomic bomb, the key is achieving a critical mass, the minimum amount of fissile material required to sustain a self-sustaining chain reaction. When the critical mass is reached, the energy released in each fission event triggers subsequent fission reactions, rapidly releasing energy in the form of heat, light, and radiation. The Hiroshima bomb is a tragic example of an atomic bomb's destructive power, where the uranium-235 core reached critical mass upon detonation. In contrast, hydrogen bombs employ a two-stage process. The initial detonation of a smaller atomic bomb, the primary, generates the necessary high temperatures and pressures to initiate nuclear fusion in the secondary stage. The primary, often fueled by fission reactions, releases an immense amount of energy that compresses the secondary, which contains deuterium and tritium. This compression triggers the fusion reaction, resulting in an even more powerful explosion. The Ivy Mike test is a striking illustration of a hydrogen bomb's working process. During the Ivy Mike test, the primary fission bomb generated the heat and pressure needed to initiate fusion in the secondary stage. The intense heat caused the deuterium and tritium isotopes to fuse, releasing an astronomical amount of energy. This multi-stage process demonstrated the potential of hydrogen bombs to unleash unprecedented destruction. In wrapping up this exploration of atomic and hydrogen bombs, we've uncovered the critical differences in their underlying nuclear reactions and working processes. From the immediate devastation of Hiroshima to the groundbreaking potential of hydrogen bombs, these weapons exemplify the astounding power and responsibility that comes with understanding and harnessing the forces of the universe. As we reflect on the history and science behind these bombs, let's carry forward the lessons learned to strive for a world where such destructive power is forever replaced by cooperation, understanding, and the pursuit of lasting peace. Until next time, keep your curiosity alive and continue to explore the fascinating realms of science.